Okay, so section 5.5 is using exponential and logarithmic models to solve word problems. We did this a little bit in 5.1. In 5.1, all of the variables were there. All of them were there. So all we had to do is know how to plug them in and do the math. This time, there's some variables missing. So if something's missing, then we have to do what we previously just did and solve to find one of the variables and then plug it into the equation. So here we have a problem that says a certain bacteria population is known to double every 90 minutes. Suppose that there are initially 80 bacteria. Write an expression that models the size of the population after T hours. So let's look at what we have here. I have A, remember? We have A, and then we have B, and then we have our exponent. Or we have continuous, and we're going to use continuous because it says bacterial growth is continual growth. So we're going to use this one. I'm going to write down what I know. I have initially 80 bacteria. So A is 80. Remember, our initial amount is 80. I have time, that is 90 minutes. But in my question, it says they want the time to be in hours. So I'm going to change that to 1.5 hours. And I want to know the size of the population after T hours. I want to write an expression for f of t. Nothing in here is giving me R as our growth rate. All I see is that it's doubling every 90 minutes. So I can find R from doubling. So let's write down what we know. I'm going to write down this formula right here. And I'm going to plug in everything that I know. I know that A is 80 times E to the R. I don't know what that is, but I know that T is 1.5. And I also know that after this 1.5 hours, or 1.5 hours, which is 90 minutes, my initial population of 80 doubles. So I know that this is going to be 160. This is 160. So I'm going to divide both sides by 80, which tells me that 2 equals E raised to the R times 1.5 power. So I can find out what R is by using to take the log of both sides or Snell this. So I'm going to come back over here. I'm just going to take the ln of both sides. Might make it easier if I write this as 1.5 times R. Now I can take this, move it around to the front. And remember, ln of E equals 1. So I'm going to put a big 1 right here on this. So I'm going to divide both sides by 1.5. So ln of 2, which is a number, divided by 1.5 equals R. So we have to remember what we're doing. It says write an expression that models the size of the population after T hours. So I'm going to use this formula. And I'm only going to plug in my A and my R and my T. I mean, not my T. My A and my R. we're writing a formula so we can plug in any kind of time and see what the bacterial growth is. So it's F of t equals A, which is 80, times E raised to the R. Where's R? This is R. Times T power. And this is our formula. Oops. Right here. So if I wanted to know how much bacteria was in there after 5 hours, then I would plug in a 5 here, and it would tell me what it grew to. Okay, any questions? All right, we're going to move on to the next one. The half-life of radium-226 is 1,590 years. If a sample contains 200 milligrams, how many milligrams will remain after 1,000 years? So let's look at what we have here. A equals 200 milligrams of radium of, yes. And what else do I have? I know that my time is going to be 1,000 years because we want to know after 1,000 years how much is left. So we're going to say the time is 1,000. And this is saying that the half-life of radium is 1,590 years. That means that whatever was in here to start with, after 1,590 years, there's going to be half that amount. That's what that means. So I don't know what R is. I do not. So let's find R. I'm going to move over here. So I know that I have 200 milligrams times E raised to the R times T power. So to start with, I have that many years. That 200 is going to become half of 200. So you can write it as half of 200, which is 100. I'm going to divide both sides by 200. And I want you to notice that up here in this problem, we said it doubles. So my F of t part ended up being a 2. And here we said it's half-life, so my F of t part ended up being a half. If we plug in our numbers, that's what ended up happening. So I'm going to take the ln of both sides. I'm going to move this around to the front. Oopsie. This is equal to 1. So that means R is going to be ln of 1/2 divided by 1590. So I found out what R is right here. I'm just going to draw an arrow. The question says how many milligrams will remain after 1,000 years. So I can use my formula Remember, A is 200 times e raised to the r. R is ln of 1/2 divided by 1590 times t power. And I want to know when t is 1,000. So I'm going to plug in 1,000. This looks absolutely horrible. That's all a number. All of this is a number. So let's plug this into the calculator. So I'm going to plug in 200 times e raised to the ln of 1/2. I'm going to use 0.5 for 1/2. Divided by 1590. And then up here I need to multiply that. Nope, that didn't work. Times 1,000. So 129.33 milligrams is what's left after 1,000 years. Oops. Approximately. Oh my gosh, why does that keep happening? Okay, so we're going to look at the next problem, which is a problem about a wooden artifact and carbon dating, which is how they find how old something is that's been buried in the ground for a long time. It says a wooden artifact from an ancient tomb contains 35% of the carbon-14 that is present in living trees. How long ago to the nearest year was the artifact made? The half-life, we just did a half-life problem, of carbon-14 is 5,703. So I do not know what R is. So I'm just going to jump right there and say we need to find R because I don't know what that rate is. So even though the initial amount is not given, we can still find R. The A is not given. We can still find R. So let's do that. We're going to write down what we know. Remember I pointed out up here that when we were talking about half-life, our F of T ended up being 1/2. Right? And that 1/2 was 1/2 of A. So I don't know what A is, but I do know that I can take 1/2 of whatever A is, and it's going to equal A, whatever that is, times E raised to the RT power. I don't know what R is, but I do know what T is. So let me highlight what I know. Half-life goes with 5,730 years. So that's going to be my T. And right here it says half-life. So we're going to take half of our original amount, which I don't know what it is. Okay. So what I can do, I can get rid of this A. Let's say that A is 100. I can divide both sides by that amount, which is going to make this cancel. So I see that 1/2 is going to equal E raised to the 5,730 times R power. So I can take the natural log of both sides, or the log, or I could snell it. It doesn't matter. But I'm going to take the natural log of both sides. I'm going to move this around here. And again, ln of E is 1. So to find out what R is, I'm going to divide both sides by 5,730. So I know that ln, I'm going to replace this with 0.5. Divided by 5,730 equals R. So I found R. I want to know how long ago to the nearest year the artifact was made. I know that I have 35% that is left of A. I still do not know what A is. So instead of half-life, this was a half, and I could have written this as 0.5 right here. That's the half-life part. This time I need to do 35%. So 35% is 0.35, and that has to be of the original amount. I don't know what the original amount is, but I can still find the nearest year because I can use my equation, which I didn't write it here, but I could. 0.35 of A, the original amount, is going to equal A times E raised to the RT power. So R is ln of 0.5 divided by 5,730 times T power. Again, I'm going to do the same thing that I did here. I'm going to divide both sides by A. And I'm going to do the same thing that I did over here. I'm going to take the natural log of both sides. I'm going to move this over. This is going to move over here, just like I did here. Times ln of E. And remember that ln of E is 1. So to find out what T is, I need to divide both sides by the ln of 1/2 divided by 5,730. And that's going to give me T right here. This cancels. This is the only thing that's left. So in my handy dandy calculator, I have a fraction with ln of 0.35 in the numerator, and in the denominator I have another fraction, which is the ln of 1/2 oopsie, divided by 5,730. And I get 8,678 and a half years. It says to round to the nearest year, so I would round that up to 9. So 8,679 years. So how long to the nearest year was the artifact made? It was made how long ago? 8,679 years ago. That's what we found out. And we have one more problem. This problem is a compound interest problem. It says find the time required for an investment of $5,000 to grow to $7,400 at an interest rate of 7.5% per year compounded quarterly. So we used this formula previously, so I'm going to write it down. This is not continuous compounding, so we have to use this one. And we did this in 5.1. So let's write down everything we know. I'm going to write it over here. A is our initial amount. Find the time required for an investment of $5,000. So our initial amount is $5,000. I want it to grow to 7,400. So F of T is 7,400. My interest rate is 7.5%, but I have to write that as a decimal per year, compounded quarterly. So remember that N, that's our number of compounds, that's quarterly. And then T is what we're looking for. It says find the time. So that means I want to know what the heck that is. How long is that going to take? So I'm going to plug in all of my numbers. I have 7,400 equals 5,000 times 1 plus 0.075 over 4 raised to the 4t power. So you see I'm missing this exponent. Just like up here, I needed to find r because that was in my exponent part. So I had to find it. Just like I did up here, I had to find this exponent part. So we know how to do that. Okay, so let's look at what we have. I have 5,000 times something equals 7,400. So let's get rid of the 5,000 by dividing both sides by 5,000. And that ends up being, you can leave it like that, but I think it's a pretty nice number in the calculator. It's not a horrible number. Let's do 7,400 divided by 5,000. And I get 1.48. So that's not a horrible number. So I can change this to 1.48. That cancels. And this is 1 plus 0.075 divided by 4 raised to the 4t power. I can change this to a number in my handy dandy calculator. So I have 1 plus fraction. 0.075 divided by 4. Yeah. I'm going to leave it as this decimal. If you get this little fraction thing over here to the side, that means that this is not a repeating decimal or a decimal that goes on forever. So I'm going to write this part in place of my parentheses. Oopsie. So now I have to think of this as the problems that we previously solved, and I need to take the ln of both sides, or I could turn this into the Snell method. So I'm just going to ln both sides because it's really easier with all these decimal numbers and these word problems. And I see that this can move around here. So I have 4 times t times this number. This is a number. So to find out what t is, I need to divide by 4 times ln of 1.01875. This cancels, this cancels. I'm just left with t. T equals whatever that is in the calculator. So when y'all plug that into the calculator, you're going to get 5.28 years. It says find the time. The time is 5.28. Required for this investment of $5,000 to grow to $7,400. So that's what we just found. We have to put that money in there and leave it alone for 5 and 1/4 years.